Hello everyone, my name is Gilles Corman and I am a PhD student from the University of Liège in Belgium. The topic I'm going to present over the next 15 minutes deals with the assessment of gas impact on clay rock integrity using a second gradient model. It is a major issue with regard to the long-term management of nuclear waste that constitutes the general framework of this presentation. Let's start with a short contextualization. Nowadays, the nuclear energy has many civil applications, among which the stable and massive production of electricity through the exploitation of nuclear power plants. As of today, this energy accounts for 10% of the global electric capacity. However, the nuclear fuel cycle generates high-level radioactive waste which are harmful to the biosphere over a lifetime much longer than the human life scale. And in this context, the deep geological disposal is considered as one of the more promising solutions for the long-lasting storage of nuclear waste. So this mode of repository is based on the multi-barrier confinement concept, which offers a succession of natural and engineered layers to delay the migrations of radionuclides over very long timescales. Practically, the radioactive waste packages are placed in steel canisters, sealed in a concrete storage gallery using a concrete backfill, and the main barrier being the clay geological formation itself. During the implementation of this solution, complex multiphysical processes are likely to occur and to affect the system and its confinement characteristics. So in the short term, the gallery drilling process causes stress redistribution that triggers crack propagation, leading to the creation of an excavation damage zone. And in the long term, the generation and accumulation of gases such as hydrogen resulting from the corrosion of the metal components of the system may potentially open preferential flow pathways for the radioactive substances. And so in this context, the numerical modeling turns out to be an effective technique to perform predictions at the timescale of the storage. And so this presentation will specifically focus on the description of a second gradient two-phase flow model capable of simultaneously processing the multiphysics couplings related to the gas migrations and the development of fractures. So here is the outline of the presentation, which will be divided into 5 main parts. And after this introduction, let's now investigate in more details the 2 ingredients of the model. First of all, with a view to representing the damage in rocks, it is interesting to observe how rupture occurs in geomaterials. Most of the time, these macroscopic fractures are caused by the formation and propagation of a failure plane that is in fact a zone of localized shear deformations. So taking a closer look at the process of underground gallery excavation, this mode of failure appears to be predominant in case of high-stress environment, which is the case in the context of deep geological disposal. And in particular, in situ observations in host rock formations like Boom Clay in Belgium or the Calovox-Fordian claystone in France attest to the development of extension and shear fractures around the galleries, leading to the creation of an excavation damage zone in the near field. From these observations, it is then necessary to provide modeling techniques capable of numerically reproducing damage as strain localization in shear bend mode. And in practice, we don't use classical finite element methods, which are dependent on the mesh, as it is clearly visible on these results of 2 biaxial compression tests with 2 distinct meshes. And instead, we have rather recourse to specific regularization techniques that introduce an internal length into the model in order to avoid the pathological mesh dependency. And this way, we can see that the shear bandwidth is controlled, no matter the mesh size. And practically, we can see that if such a technique is used to model the damage in Boom Clay and in the Calovox-Fordian claystone, we obtain a good agreement with the extension of the damage zone that has been conceptually validated in these 2 host rock formations. On the other hand, the mechanisms of gas generation and migration must also be integrated into the numerical model. And practically different modes of gas transport can occur depending on the rate of gas pressure increase. So for small injections of gas, there is advection and diffusion of dissolved gas within the liquid phase. If gas pressure increases, a gaseous phase is formed, giving rise to a two-phase flow. And if gas pressure keeps increasing up to the fracturing pressure, then it initiates preferential flow pathways. And finally, in case of accumulation and strong pressurization of gas, then irreversible fractures with a single gas phase flow can be created. And on top of that, the interactions between the damage and the transfer properties must also be taken into account by integrating specific hydromechanical couplings into the numerical model. So let's now continue with the description of this numerical model. Basically, the rock environment surrounding the storage system can be seen as a triphasic porous medium, which is composed of three species, namely mineral, water, and hydrogen, distributed in three phases, namely solid, liquid, and gas. And in practice, it is assumed that the solid phase corresponds to the mineral species, and that the gaseous and liquid phases both comprise water and hydrogen species in different forms. The rock environment surrounding the storage system can also be subjected to strain localization in the form of shear bands, leading to localized rupture under heavy loading. And so to properly model these localization processes, a regularization technique of the second gradient type is implemented into the model. And this technique proposes to enrich the kinematics of the continuum medium with the microscopic effects. So basically, this means that the macroscopic medium includes smaller particles at the microscopic scale, thus defining fields of displacement and microscopic deformation in addition to the general description at the macroscopic scale. And finally, to accentuate the interactions between the transfer properties and the damage, additional hydromechanical couplings have been integrated into the model. And so on the one hand, a power cubic formulation is used to model the strain-dependent evolution of the hydraulic permeability, which allows to generate an increase in permeability within the shear bands. And this phenomenological law can be fitted on in-situ measurements. On the other hand, a strain-dependent evolution of the water retention curve correlated to the evolution of permeability is also used to account for the modification of the pore network morphology due to damage. And with these ingredients implemented, we obtain the second gradient two-phase flow hydromechanical model, which allows to consider the interactions between the gas transfer mechanisms and the fracture opening. And if we take a brief look at the framework of this model, then this model is governed by these three equations. There is first the balance of momentum for the mixture, where the microscopic effects are introduced through the double stress. Then the second equation is the water mass balance equation, where water is considered both in the form of liquid water and water vapor. And the last equation is the gas mass balance equation, where hydrogen is similarly present in the form of dry hydrogen and dissolved hydrogen. And in these last two equations, a term is linked to the mass flux, and another one is linked to the variation of storage, with Q being the source term. In addition, the model incorporates the features of two-phase flow transfer approach, in which the fluid mass flow is made of an advective component of each phase according to Darcy's law, and a diffusive component within each phase according to Fick's law. This brings us to a type of application that can be tackled using this model. So the treated application deals with a medium activity and long-lived waste storage gallery set up in the Calo-Vauxfordian claystone following the French concept. The rock environment is supposed to be an elastoviscoplastic material made of bedding planes with an horizontal orientation. And the structure is composed of 3 layers of support for an internal usable radius of 4.35 meters. This figure gives an overview of the mesh of the model in plane strain state, with all the initial and boundary conditions required for the simulations, and only a quarter of the domain is considered due to the symmetry condition. Basically, the simulation takes place in 3 phases. The excavation phase is first simulated according to the deconfinement profile, and this phase is completed by the installation of the different layers of support. Then the gallery is filled during the operation phase under ventilation, which generates a strong suction in the system. And finally, once the storage drift is supposed to be properly sealed, then there is a period of pore water pressure stabilization before gas migration in the form of hydrogen pressure variations following the given profile. Moving on to the main results, main numerical results, we can first observe a global convergence of the drift during the excavation phase. And in parallel, the deconfinement applied at the intratus of the rock mass leads to the progressive development of a damage zone, which is characterized by clear localized shear bands. The role of the second gradient elastic modulus D in the proper representation of the shear bands and in the control of the bandwidth can be highlighted by considering a value 10 times higher for this specific parameter. It follows that considering a higher value, higher internal length scale for the model, then it tends to homogenize the development of the shear bands, attenuating this way the initiation of local intense bands in the present case. And furthermore, this comparison with non-supported gallery excavation shows that restraining the convergence of the drift inhibits further growth of the shear bands. And as a consequence of the creation of a damage zone, the transfer properties are progressively affected in the vicinity of the drift, with an increase of about 2 orders of magnitude of the permeability, and in parallel, a global drop of the value of the gas entry pressure in the near field. Finally, if hydrogen is injected, a slight desaturation of the rock mass is noted for the peak of hydrogen pressure. And at this time, dissolved gas in the water phase is not sufficient enough to ensure the hydrogen transfers, which leads to the creation of a distinct gaseous phase in the desaturated zone. And if an increase of impermeability with strains is considered in the simulations, then we can observe that hydrogen tends to enter the first meters of the rock mass much more easily with respect to the reference simulation. And if an evolution of the retention behavior with strains is additionally considered, then a distinct gas phase emerges for the largest amount of hydrogen, leading to a rapid desaturation of the damage zone. And it follows that hydrogen propagates easier and faster across the whole damage zone, which is more in line with in situ observations. This is now time for the conclusions, and we have seen that the geological disposal for radioactive waste is a seat of complex multi-physical processes that can interact with each other. Accordingly, we have developed a second gradient two-phase flow coupled element able to model the damage around the underground structures with strain localization in shear band mode, and also able to reproduce the mechanisms inherent to gas migration while taking into account all the related hydromechanical couplings. And then, using this model, we have shown that the obtained fracturing pattern is in good agreement with the experimental observations, and that the flow properties and transfer kinetics are affected in this damage zone, leading to the faster propagation of gas around the system, which is also in line with in situ observations and constitutes also the major contribution of this research. So that's it for my presentation. I would like to thank you all for your attention and to address also a special thank to the BIOT project for the funding of this research. Thank you.